Okay, good afternoon, and thank you everyone for joining us for another Jane Irrigation irrigation training series. I'm Richard Restucia, Vice President of Water Management Solutions for Jane, and I'm really excited today to talk about pumps. And the reason I want to talk about pumps, or why I think it's so important, is really for almost all the irrigation that goes to ag or landscape irrigation, it really has at some point traveled through a pump. But I certainly think that, especially in the landscape industry, pumps might be one of the subjects that people know the least about, or one of the subjects that hasn't gotten enough attention or as much attention as it should have. And so today we've got a real pro helping us out with this. Our guest today is Robert Aldinger, and he's the Regional Manager for Engineered Systems Division of Precision Pumping Systems in Boise, Idaho. Now, that's a long title, but the real good news is he's been involved in designing and helping people set up and, more importantly, run pump systems for about the last 25 years. I think if you ask around and talk to people about who's great at troubleshooting, who knows what they're talking about when they're sizing a pump or troubleshooting a pump, you're going to find out that many people will say it's Rob. So with that, I want to say welcome, Rob. And I also want to say, Rob, you heard what I said about not understanding pumps as well as we should in landscape. I'm just wondering why you think that is.
Well, my experience has been that all of you out there have some specialty that you invest most of your time and energy into, and it tends to be everything that happens after the pump. So in many cases in the irrigation industry, you're probably, you're tapping into a municipal water line and you're getting your pressure and your water from there, or you might be tapping into another pump that's been put there by, by somebody else. But in very few cases are you probably spending a lot of time with the pump. Having said that, you're highly likely from that point on to be spending more time with the pump. And so the kind of the hope here today is to give you a little bit of better understanding as far as how those pumps function and how they operate, and so you'll be a little more comfortable with them in the future.
Yeah, that would be great if we could come away with that understanding. That would hit the nail right on the head. So thank you.
All right, so I'm going to just, as he said, I've been doing this for a long, long time. It's about the only thing I think I know anymore. But I think that I and everybody in this building know this pretty well. So what I'd like to talk to you about is most common pump, in fact, probably the only type of pump you're ever going to encounter in the irrigation industry, which is known as a centrifugal pump. Okay, and I'm going to go through some slides here. And these slides are going to essentially explain the functionality of a centrifugal pump, motors, etc. And I'm happy to entertain any questions along the way. In fact, that's my preference. And if anybody isn't quite clear on what I'm trying to convey, please let me know. So the centrifugal pump, as you've seen the outside of centrifugal pumps, but everything that goes on with a centrifugal pump actually happens on the inside of it. And every centrifugal pump has what's called a pump impeller. And the pump impeller spins around and essentially moves water, converts a constant energy source to a variable combination of pressure and flow. Lots of words there. And since the energy is constant and the pressure and flow are variable, when the flow increases, the pressure must decrease, or vice versa. So if you look at that little graph down below there, you'll see that is what that's indicating. If you move to the right on the flow, which is the bottom axis, you'll see that the pressure, which is the vertical axis, decreases. If you move to the left, the opposite happens. That is what's known as a pump curve. Every pump that's ever been built in all of history has a pump curve that you look at, and every pump has some limited range of performance. That pump curve indicates what that performance is intended to be. If the flow and pressure you're looking for doesn't exist on a specific pump curve, then you need to move on to a different pump. All right?
So pump curve should be one of the first things we're talking about as we start thinking about sizing and getting a pump for a project.
Right. So you're not going to, if you're looking at sizing a pump, you're not going to do anything but that. Immediately, you're going to go to a catalog of curves, go on a computer or whatever, These days, it's mostly on a pump selection software online, and you go on there and you type in what your pressure and flow essentially, and it will give you a list of pumps and show you some pump curves. You try to find the one that's most efficient for your operation. That list, you're going to see a list of them because every single pump was designed to cover a specific operation range. There's no such thing really as an all-purpose pump out there.
Yeah. Okay. And then the impeller, that's powered by a electric motor. Is that right?
It's powered typically in irrigation applications by an electric motor. There are other methods, but for the most part, today we're going to talk about electric motors only. And for the most part, with the exception of large scale, maybe agricultural irrigation applications, you're only going to see electric motors being used.
Right. So, and then, yeah, and I've seen Jane use some solar powered pumps too, but that's still electrical, right?
That's still electrical. You're still going to have electric motors. That's another topic for another day. We could talk a lot about that as well, but we'll, yes, and we're seeing more and more of that actually.
Yeah. Okay, great. Thank you.
You bet. So the centrifugal pump impeller is essentially spins, and when it spins, it creates a low pressure zone in the middle of the pump. If a centrifugal pump impeller is spinning and there's no water present, it will not pump water. So if there's no water in the center of that impeller when it starts to spin, it will never pump water. It will simply spin round and around and get really hot and eventually damage itself. That's what's called loss of prime. I'm sure many of you have heard that term. That's what's happened if you've lost prime on a centrifugal pump. Impeller starts to spin, and essentially a centrifugal force forces the water outward, moves the water and adds the pressure to it. The diameter, speed, and vane width are what affect the output of a pump. And that's also what's going to affect, or what's going to affect which pump curve you're going to be looking at. The only thing that they've changed on a pump in order to change the curve is 1, 2, or 3 of those things. So that's the impeller diameter, it's the speed of the pump, and the width of the vane that determines how much water that water is going to move and at what pressure. And here's your standard, the most common pump in the world, an end suction centrifugal pump. I'm sure everybody that's watching this today has seen one or many of these. It's got the impeller inside what's known as a volute. Water comes to the center of that impeller, or water needs to be at the center of that impeller when it starts to spin, and it forces the water outward. There's the motor, and there's the shaft that connects to the pump. The common misconception is that a pump and a motor are essentially the same thing, and the reality is pumps are manufactured by pump manufacturers and motors are manufactured by motor manufacturers, and they're coupled together. So they're not, so they're two separate entities. Typically used for suction lift and pressure boost applications. The pros of a end suction centrifugal pump are they're relatively inexpensive, they're easy to repair and replace, and common parts are easy to find. The cons, of course, is they're subject to prime loss. If that pump is in a suction lift application, which we'll talk about in a minute, and it needs to draw water from a source lower than it, it's highly likely to lose prime. So if you have an automatic irrigation system and your pump tends to lose prime, all of the automatic that you have in your irrigation system is now gone away. Somewhat less efficient than other types of pumps and not suitable for very high pressures. And when I say very high pressures, I'm talking about pressures well into the 100 PSI range. Yeah.
So when you lose prime, what do you have to do? How difficult is that to repair?
Well, it depends on the application. So you want to so if it's a suction lift application and you're pulling water out of a pond or something below the pump, there should be what's known as a foot valve on there. The foot valve is essentially a check valve that's in that water source. So once you're able to draw water up into the pump, which you can do a number of different ways, you can have their vacuum priming pumps. You can just simply put water in there until it reaches that pump. Once it, once that water is in there and you have a foot valve, barring any complications with the valve being stuck open or something, the pump should remain primed from that point on. that's probably the most common way to do that. Again, there are other automated methods of priming pumps, but in any case, if you're pulling water from below, you definitely want to have a foot valve in that water source.
Yeah. So it's easy to take care of if you're there at 4 in the morning when the pump comes on and your irrigation's coming on, right?
Absolutely. In fact, I've seen a lot of golf course superintendents who sleep in their pump house when things aren't working properly. So
yeah, I bet.
If that's something you want to do, and some of them maybe do, that's probably okay, but not very many people want to do things that way. So back to that impeller again. Spinning forces the fluid outward. A low pressure zone is created in the center of the impeller because the water is being forced outward. And this kind of gets into the weeds a little bit. We're not going to go very far, but the reality is, and this is a geeky pump joke, but pumps don't suck, all right? And people always think pumps are right, and they even call it an end suction pump. It's not in reality sucking. The pressure in the center of that impeller has to be lower than whatever the atmospheric pressure is, and the atmospheric pressure forces the water into the pump. So again, we can go deeper in the weeds another time, but we'll probably steer clear of that unless anybody has any questions. Okay, so this is a suction lift pump station. Typical application. So the atmospheric pressure is forcing that water, pushing down on that water. There's an intake screen with a foot valve there. When the pump starts to move, the pump draws the water up into the pressure actually forces it into the center of the impeller, which then forces it out into the irrigation system. Yeah.
Hey, so Rob, we had a question coming in from our audience, and the question is, how do I know if my pump loses prime? Do I get a message, alert? How do I know this?
Well, that gets into various methods of automation. If you've got a pump that sits on that's bolted to a log and, you turn it on and off, you're going to know it's not prime because it's not pumping water when it's on, okay? We can go all the way through to, you've got all kinds of sensors available, and you've got remote control and monitoring available. And if your pump loses prime, you'll be notified via your cell phone or your computer or whatever. And then there are all points in between. The most obvious is if your pump's on and the water's not, there's no water running, turn it off because it's going to burn up. So yeah, I hope that answers the question.
Yeah, so that's great. Yeah, James got some great products for that. JaneLogic Pulse will let you know if your pump's running when it's supposed to be or not, or if you've got a problem. So, yeah, thanks, Ron.
Bet. So a flooded suction pump is an in-suction centrifugal pump whose water supply is being supplied to it by an above-ground source. So not only is there atmospheric pressure pushing the water into it, but there's also the head of water above the pump. So in this case, would be coming out of an elevated tank, so that the water pressure or the atmospheric pressure and the water pressure pushes water into the center of the impeller, and then again the pump adds the pressure to it and forces it out into the irrigation system. A booster pump application is when there's an already pressurized source, typically another pump somewhere, that's going to be providing pressurized water to the pump station. But if you have a large, sports field, something like that, that has irrigation equipment out there that requires higher pressure than is available from that source, then you add what's known as a booster pump, and the booster pump adds the additional pressure to go out to the irrigation system. Okay, that's also known as pumping in series, which we're going to get into here in a second. So here are just some examples of package pump systems. Package pump system, there are two ways to install a pump system. There can be either built on site, pipes, valves, pumps, control system, etc., or there are many people in the package pump system manufacturing industry, ourselves included. So you get your pipes, valves, and so on are built and assembled here. This is using multiple pumps in parallel. We'll talk about that in a minute. And the control system and everything is integrated, and the system is pre-tested prior to leaving our facility. So when it gets to the site, all you do is hook up the pipes and put power to the pump panel, and all of the automation and everything is ready to go.
Sounds like the way to go.
Well, in majority of applications, yeah, we believe it is the way to go. Occasionally, there are applications where the alternative is maybe the better solution. So just various shapes and sizes of package pump systems for in-section centrifugal pumps. So now I mentioned a minute ago, pumping in series. So pumping in series is when one impeller pumps to another impeller, maybe to another, maybe to another, maybe to another. So what happens when you pump in series is the water that moves through each impeller, the amount of water that the first impeller produces is going to be exactly the same through every impeller. Every impeller only adds pressure, it does not add flow. So in this application, we have 100 gallons a minute going through that impeller at 50 PSI. When it goes through the next one, it's now 100 PSI. And when it comes out the final impeller, it's 100 gallons a minute at 150 PSI. So pumping to a pump is known as pumping in series, okay? You may have seen vertical turbine pumps in application. Vertical turbine pumps tend to be pumps pumping in series. If you look at the bottom of that, you'll see that there are multiple impellers in a single pump. Those are essentially pumps pumping in series, adding pressure through each one. There's the pump suction. There's a shaft that goes to the motor on top, so the vertical turbine pump has its impellers submerged in the water source. Typically in a well casing, water surface is somewhere above the pumps in the well casing, and when the pump comes on, it forces the water up the pump column and out. These pumps are also oftentimes used in open bodies of water in the same way. Instead of a well casing, it could be a large wet well or in a pond, etc. Again, if anybody has any questions, please let me know. All right, so here's a couple of applications of pumps in a wet well.
Yes, we have another question here, Rob, and the question is this, right? I mean, we've really touched on a few different pumps now, a few different designs. How do I know what I really need?
Well, yeah, that depends. I would say I'm going to talk a little bit about why we've kind of transitioned into vertical turbine pumps here. Vertical turbine pumps tend to be for higher volume systems for the most part. By higher volume, we're usually getting into the several hundred gallons a minute, and also for higher pressure systems. Since we're pumping, in series, we have the ability. An in-section centrifugal pump, because you're limited by physics, can only produce so much pressure without pumping into an additional impeller. So with a vertical turbine pump, you can put as many impellers as you want in there. They're called stages. So generally higher flow, higher pressure applications for vertical turbine pumps.
So typically I see the vertical turbine pumps on ag applications, right? And I see them a bit on golf courses too, don't I?
You do, and so on ag applications, it's primarily an issue unless you have some elevation that you have to deal with. It's primarily going to just be an issue of volume with vertical turbine pumps, because in ag applications, if you're pumping into pivots or you're pumping into hand lines or multiples of those, they're usually very high volume systems, thousands of gallons a minute in many cases. Golf courses, essentially the same thing, usually, very large volumes, but also higher pressures. So in ag applications, you can get away with, 40, 50 pounds. Golf course applications, you tend to be well over 100. So,
right.
Large parks, large sports complex, things like that, that's typically where you're going to see vertical turbine pumps.
So, and then for commercial landscapes, most commercial landscapes, the question here is a booster pump going to be what we're typically dealing with, or actually you need a booster pump with another pump, right?
It's dependent on probably the location more than anything. And around here, we have large commercial applications and subdivisions, et cetera, that utilize surface water, i.e. canals and ponds. For their irrigation water, they don't tap into the potable water system at all. So we use a lot of very large vertical turbine systems around here. In most cases, particularly in urban areas that are already developed where that's not possible, you're primarily going to see booster stations because the pressure available from whatever your potable water source is not going to be enough to run large heads, et cetera. So pumps are submerged. Again, if the pumps are submerged, then you don't have the issue of losing prime. So that's another good application for automatic. If you have your automatic irrigation system out there and you don't want to lose prime, if you can submerge the pumps, then you don't have to worry about that. Higher initial equipment costs and installation costs with vertical turbine pumps. So if it's if it's a lower flow, lower pressure application, it may not be the ideal solution in that case. Pre-filtration, if you're coming out of a surface water source like a pond or a canal or anything like that, pre-filtration before the water enters the wet well is, I would say, not only highly recommended, but required in order to make sure that debris doesn't get in there that plugs up your pumps. If you have vertical turbine pumps and they get plugged up, you have to hire a crane. Crane has to pull them out vertically, so it can get very expensive.
Yeah, truly a pay me now or pay me later scenario, right?
Right, right. And it's one of those things that does get left out in a lot of applications. And I think everybody that's ever left them out has probably wished that they hadn't. So we're going to move on here to show you some examples of some packaged vertical turbine stations. Essentially, the concept is always the same. Take all of your motors and your pumps and your valves and your filters and your control panels, and you integrate them all in a facility. Then you test them all. And then when the package arrives, very little assembly is involved, and you hook up your pipes and hook up your control panel, and you're ready to go. As you can see, we have a lot of various applications here.
Yeah. So
go ahead.
So Rob, I don't know if you're going to touch on this in a minute or not, but what about the maintenance of all these? Is it all the same? Are you doing about the same things? How do you maintain all these pumps?
No, you're not doing the same thing. And I would, after 25 years in this business, I would recommend for most users to hire professional maintenance companies to maintain your systems if at all possible. They can be complex, and there's a lot of things that if they're maintained properly and you can keep your eyes on them and keep an eye out for problems, you can avoid any catastrophic failures. If they're not maintained properly, it's pretty common for, the day when it's 112 out and you just put your new sod down for the system to fail on you. There's some, there's a lot involved in it. I'm just going to say that.
Yeah, so the maintenance, it's a monthly, quarterly, annual that they come out and do. They charge you by the visit, or do you sign a maintenance contract? What's that look like?
Well, we here we have a maintenance contract, which is typically in our climate where you have winter, and so you're going to have to winterize. We have a spring startup in which we start everything up, go through all of all of the controls and everything, make sure everything's in good shape. Stop in once or twice a year, depending on the application, and then do the winterization. And you do that repeatedly. That would be a maintenance and service program. Typically, that's what I would recommend. In climates where you never shut down, even more important, because you don't have that turning it off and turning it back on again, where you're just by virtue of that, you're forced to go through that process. So I would recommend, always, if at all possible, to hire a good, solid pump company locally to do that.
Great. Yeah, thank you.
So just quickly, submersible turbine pumps, not as commonly used, but a submersible turbine pump is really identical to a vertical turbine pump, except for the motor is on the bottom of the pump and is underwater, intended to be put in well casing. So your submersible, rather than the motor being above ground, it's underwater. Nice thing about these in many applications is it reduces the noise if that's an issue. So there's your, you got your motor, your shaft, and your pump section on the bottom, and then your impellers, your stages, i.e. pumps pumping in series on the top of that. Then they pump it up to above ground and out to the irrigation system. Typically used in wells, but they can also be used if they have the appropriate protection around the pump in wet wells or open bodies of water. So this would be an example of a submersible pump system, very similar to the vertical turbine pump system, except for you can see that the pumps and the motors are actually underwater in this case. Also, in lower horsepowers, I say up to about 30 horsepower, significantly less expensive than vertical turbine pumps, and you still have the advantage of the pumps being underwater, so the impellers are submerged, so you cannot lose prime.
Yeah, so Rob, we have another question about maintenance. And that is, maintenance, regular maintenance is very expensive. Is there things that a pump owner can do to kind of reduce that maintenance? Stuff they could do on their own to kind of extend the life of the pump or reduce the maintenance? Some of the things they could do on their own.
Yeah, so I think one of the most important things you're going to see is where the shaft of the pump attaches to the motor. There's a transition from an area that has pressurized water in it to a motor that needs to remain dry. At that point, there's some sort of a seal, either what's known as a mechanical seal or what's called packing. To properly maintain and ensure that those are working right is there's a fair amount to that. We will be actually posting on our website here shortly instructions for how to do that on virtually any pump anywhere. That's really important. That's one of the causes of big problems is when those shaft seals start to have problems and they're not maintained or tightened properly. That I think is really important. Honestly, keep things clean and keep an eye on the output of your system. If it's not doing what it used to do, you assume you probably have something going on. Don't let it get worse. That would probably be a time at that point then to call somebody. There's some limited amount of lubrication you can do as well. I'm going to warn you against ever lubricating a motor because there's very special lubrication in there. If you put the wrong stuff in, you're buying a new motor. So, but other than that, doing those things, keeping an eye on the performance and noticing any noises that are not usual. Again, probably time to look more closely at some things.
Yeah. Okay. Great suggestions. Thank you, Rob.
Yep. So the submersible turbine pumps, and we'll go through that fairly quickly. Same thing, package systems. I don't want to take up too much time on this. You're going to see these vertical multi-stage pumps, quite a lot out in the field right now. And honestly, our opinion on this is never use these pumps if your water is dirty, but they're being installed out there on a regular basis. They're essentially above ground vertical turbine pumps, if you will. So you've got your pump and your motor, and inside of that you have a number of impellers, i.e. pumps pumping in series, except they're not submerged into the water source. So the water goes into the intake, it is forced through those impellers, and it goes out the other side. These are typically used for high pressure applications in irrigation pumping. These pumps are very susceptible to problems if there's any kind of debris in the water at all. We tend to shy away from them whenever possible, to tell you the truth, but we use them where there's really no other option. So we just want to, one of the things too that we've seen these misapplied is they're not well suited for suction lift. They do not effectively, and they were never designed to draw water from a source lower. They need to either have flooded suction or pressurized suction. They were always intended for boosting. So if you see these maybe designed in a project that has a suction lift, I would probably be asking some questions. Best option for high pressure boosting, fairly compact, ideal for tight spaces. And then all of the warnings, they're difficult to service, they don't seem to last very long, and have a high potential for clogging. And then having said that, as you can see, we and a number of other manufacturers build them, but I will tell you that we have majority of what we build here for potable water only sources. So with respect to sizing pumps, really quickly, essentially what needs to happen when you size a pump, we're not going to go through all of this. You need to size a pump for the most extreme requirement out there. The highest elevation, the farthest away, the largest zone. Pumps can handle anything less than that, but you can't produce more than the pump's able to produce, so you want to design for the maximum performance required on the pump. Now we're going to talk about pumping in parallel really quickly. Before we talked about pumping to a pump, which means that those pumps each produce pressure but don't increase the flow as they go from one to the next. Pumping in parallel means that pumps are pumping into a common manifold, separate pumps, and each one of them produces the same pressure, but increases the flow. So pumping in parallel, individual pumps in a common pipe, each adds capacity, but not pressure. So we got 100 gallons a minute at 50 PSI from the first pump. When the next one comes on, we have another 100 gallons a minute at 50 PSI. When the next one comes on, we have another 150 gallons or 100 gallons at 50 PSI, and our output is then going to be 300 gallons a minute at 50 PSI. So sort of the reverse of how pumping in series works.
Ah.
So this is an example of, as you've seen a lot of these, multiple pumps on a system. Each of those pumps is brought on when more capacity is required.
And the reason that works is because the output pipe is 3 times as big as the individual pipes on each one of the pumps. Is that correct?
Well, no, sorry. No, it's really an issue of you're going to, as your demand increases in the system, you're going to need to add capacity. So yeah. Generally, if you have a 5,000 gallon a minute system and you might sometimes only pump 500 gallons a minute, you don't want to use a single 5,000 gallon a minute pump in the application, because in the low end of that, they operate very inefficiently, and there are various other issues that can come up with that. So you want to phase pumps in as your demand increases, so that the system can run more efficiently. Is really the rationale behind that. And in many cases, so you have a little bit of redundancy as well.
Yeah. Okay, good. Thank you.
You bet. So I'm going to talk just a little bit about pump controls here. We all know the simple way to turn things on and off, right? We probably do it on a regular basis in our house. You can plug something right in. You can flip that switch on the wall. When you're doing this, the device you have your hand on is in direct contact with the opening and closing of that circuit, which, for low amperage applications like a light bulb or whatever, is not terribly dangerous. But when you get into larger equipment like pumps, there's a lot of energy there and they can become very dangerous. They use a device called a magnetic contactor. So now what you're going to do is you're going to flip a switch that's a low voltage switch that will cause this contactor to lock down a magnet, which closes the high voltage switch, which turns on and off the device, so that you're not making contact with that dangerous circuit. Okay? Eliminates the risk of electrocution.
Yeah, that's a pretty nice safety feature right there, isn't it?
Yeah, well, yeah, oh yes, absolutely. When you start a pump with a device like this, there are only 2 speeds. There's either full speed or stopped. You get everything that pump has, or you get nothing at all. And when it starts fast. It goes from 0 to 3,600 RPMs or whatever the pump is. And when it stops, it goes from 3,600 RPMs to 0. So you get everything or nothing with a pump when you do that. Okay? So there are a number of ways to start a pump like that. There's manual starting. You go over, you push a button, and then you're going to run your irrigation system. Often used actually in agricultural irrigation. Again, you have 2 speeds. You get everything it's got, or you get nothing. Pump start relay. Probably a number of us have seen these, where when the irrigation controller comes on to start an irrigation cycle, it has a relay on it that then sends a signal to that magnetic contactor we saw, which starts the pump. And here again, you get full speed or nothing. And now we're going to talk about a variable frequency drive, which is becoming probably more the norm than the exception on almost every pump system you're going to see out there. Variable frequency drive automatically starts, stops, and varies the speed of a pump motor to regulate the pump output. Okay? So in most cases, what we're trying to do in irrigation is we're trying to, no matter what the demand is on the pump, and remember I said you have to design the pump for the maximum output, but you may have zones that go on and off that are significantly smaller than that particular zone, and you don't want the output of the pump to be full speed because you don't want that pressure to rise, as we saw in that pump curve. If it's a low flow compared to your overall flow, your pressure is going to go very high. So we use a device called the pressure transducer, which is feeding pressure information back into that VFD and telling it to start, stop, speed up, or slow down to maintain exactly whatever pressure that we set it at. Okay? So you get a constant pressure at varying flows. Now, we also use what's known as a programmable logic controller in everything that we do, and that's the computer that controls all of that and very much more. But it also allows you to have a very easy to use, user-intuitive touchscreen to control your system, so that you don't have to try to get into the keyboard of a VFD, because if you've ever seen one, they're very complicated. Okay.
So does this help reduce the amount of wear and tear on your system?
Well, it will, you know, anytime, and this graphic we're going to see here right now is going to be indicative of that, as far as both wear and tear on the pump system and the irrigation system out in the field. So in this case, we're working with a system that was designed to be, maximum design was 50 gallons a minute at 50 PSI. Here's what happens when you turn that on. Just that fast. It goes to 50 gallons a minute at 50 PSI. If that's your demand in the field, if you've got 50 gallons a minute demand in the field, you turn that pump on just like that. That's how fast 50 gallons a minute is going to be coming out, and you're going to get water hammer.
Yeah.
Because when you turn a pump off and there's nothing to keep that main line pressurized, if there's any leakage at all, eventually you're going to get air in there to replace the water that's leaking out. That's when you get the water hammer. So now, what if we have an application where that pump's called to turn on, but the demand is only 10 gallons a minute? Now remember, we want this thing to run at 50 PSI. Again, we go turn that pump on full speed, boom, comes on that fast. You now have 10 gallons a minute, but it's at 100 PSI because that's the way the pump operates. You know, lower flow, higher pressure. You now have water hammer and your overpressure, okay? In a variable speed application, the pump curve, which is what we're about to see, it's not curved at all. So when you go to turn that first 10 gallon a minute, when you turn on a zone, VFD automatically recognizes the pressure drop, and it speeds up like that, just enough to give you 10 gallons a minute at 50 PSI. Now you put on another 15 gallon a minute zone, it recognizes that pressure drop and does that. Now you're 25 gallons a minute at 50 PSI. Still using the same pump we were using before. And finally, you turn on another zone and you're 50 gallons a minute, and your pump was 50 gallons a minute at 50 PSI. As things turn off, the whole thing happens in reverse order, okay? So a variable speed pump curve, I think the important thing to remember is it's not curved at all.
Yeah.
Right? So the only
that makes it really easy to see, you know, why they're so popular now.
Yeah, well, it also eliminates a lot of problems that happen with pumps. You know, if a pump overpressures, in many cases, there should be a device on there to ensure that it doesn't cause any damage. So you'll have a device on there that will shut it down. If it underpressures, you'll have so you can get it eliminates a lot of faults. It eliminates not a lot of problems. But you know, imagine if the other thing that a VFD does is it keeps your mainline pressurized at whatever the operating pressure is all the time, even if there's no demand. A mainline that where the pressure fluctuates a lot, you know, the fittings are moving around, there's water hammer, etc. Tends to be pretty hard on them. If you keep a mainline fully pressurized all the time, there's very little movement in the system. So this is just another example of a pump system. In this case, it's 300 gallons a minute. Was the design point, but what I wanted to point out here, if you look at those two curves, you'll see the top curve is 1,770 RPMs. That's the maximum speed of this pump. It's an 1,800 RPM pump. You'll see that the next curve down is 1,700 RPMs. In this application, the VFD has slowed that pump down to 1,700 RPMs in order not to exceed 100 PSI at 300 gallons a minute. But now the curves you see below are the energy usage curves, okay? So at full speed, this pump would be operating at 1,770 RPMs, would be utilizing 25.4 horsepower. But at the same design point, it's using 22.5 horsepower. It doesn't seem like a lot, but as that goes down, the energy usage is decreased. So that's how a VFD helps to save energy as well.
Yeah, so I could probably expect longer life out of a pump, a VFD.
In most cases, yes, because the other thing that'll happen with a pump that may start and stop at full speed is it's going to frequently do what's called short cycling if it's a pressure activated pump, which means it will turn off on very quickly reach its design pressure and turn off, and then turn on and turn off. And it's called short cycling, and short cycling is the most damaging thing you can do to a pump and motor. So we're, it looks like we're right at about, we're time-wise where we wanted to be, and we've kind of covered the material that I wanted to cover here. I think it's important to note that, you know, if you're using a VFD, all of those operations that we saw are 100% automatic. So the intention with the VFD is to have you set your pump station and forget it. So that when you're turning, whatever happens out in the field, it automatically reacts to it based on the pressure that it's sensing in the mainline.
Yeah, so I want to say, Rob, thank you. I have not, I've heard a lot of pump presentations. This one was the most clear and easy to understand that I've heard. So thank you very much for presenting that. You know, we're getting a few people in the chat now just saying amazing info. So I think you really helped a lot of us today understand pumps better and have a better idea of how to deal with them going forward. So anyway, I did want to say thank you again for presenting today. We really appreciate it. We'll be sending out an email this afternoon with Rob's contact information on it, as well as a recording of this presentation. So if you have additional questions, you can follow up with Rob. Thanks to all of you for joining us today. We really appreciate it. And I hope that everybody goes out and has a nice, safe, enjoyable weekend. Thanks again, Rob, and thanks everybody.
Thank you. Appreciate your time.
All right. Thank you.